problem. I will quickly go through this multicolored cube problem so that we can have the connectivity to the next topic. The multicolored cube problem is that there are 4 cubes. Each cube has 6 faces and 3 pairs of opposite faces. Because the face which if I am seeing one face, you would be seeing the other face, which obviously is associated face, and there are the 3 opposite pairs of faces, and each face is colored differently. The problem is to put the stack the cube one above the other such that 4 colors are visible on every face. On every face, 4 colors are visible. That's the problem. I shall not go through the details, but only thing is that what I'm trying to tell is each cube, this is unfolded, all faces are visible. So here the circular marks indicate the color code of each face. So the red color, red color, red color, yellow color, green color, and blue color. And like that, there are 4 cubes. And for every cube, I just now mentioned that a pair of opposite faces shall indicate an edge, and all the 4 colors shall indicate the 4 vertices. Okay. So a cube has 3 pairs of opposite edges, 3 pairs of opposite faces. Therefore, there shall be 3 edges in the graph, 4 vertices and 3 edges. Right. So we will be first constructing the individual graphs. To recall again here, you can see here this is one opposite pair is red to red, therefore there is a self loop over here, and another is red to green, there must be an edge from red to green, and another is yellow to blue, there must be yellow to blue. And you can now see that this graph is not a simple graph, it is a general graph because it has got self loop, number one. Number two, this graph is not a connected graph, it's a disconnected graph with these 4 vertices, right? So similarly, you will be constructing the individual graphs for cube 2, cube 3, and cube 4. So just now we have completed the union operation, intersection operation, all those operations. Now we will superimpose all these graphs. In other words, I will be conducting a union operation of all these 4 graphs. The union operation gives this graph. Then, as we discussed earlier, we have got to find out one subgraph which contains all 4 vertices, because I want 4 colors to be visible, and I want all these 4 vertices, the 4 colors, to be connected by 4 edges, and each edge from a particular cube. Therefore, all cubes should be participating. Well, then you find out how to get this, how to extract this. And now my question would be, how to automate this work of extracting this, okay, satisfying all these conditions. Then once this is extracted, we have got to remove this from here. So this G minus this subgraph should be done, and once you do that, you will get the resultant graph. This is what it is. And then this from here, I shall get for another pair of opposite faces a similar subgraph, where it should have all the 4 colors, and all 4 colors, 4 vertices should be connected by 4 edges, each edge from a cube. Therefore, is that possible? In this case, it is possible. It has been shown to be possible. Therefore, we can have all the 4 faces with 4 different colors. So this is where I had stopped, and this shall be the first topic for this particular assignment number 4 also during this period. Now, what you have got to observe here, you have done union, you have done intersection, you have done some specific operation to trace this particular contour, to trace this particular traversal. Okay, let us see what type of different traversals are possible, and after tracing, how to remove it, which is again another graph theoretic operation. So we are trying to traverse through a sequence of edges in some specified manner. So that's the topic now I shall take up. So before that, one point in the previous, you have seen that this is a subgraph of this graph. This is a subgraph of this graph. Whereas these 2 graphs, all vertices are common. Between these 2 subgraphs, all vertices are common. However, between these two subgraphs, no edges are common. All edges are entirely different, right? So now we shall formalize all this in the next session. So subgraphs. If G is a subgraph of G, see, recall, already we have told that the graph is a set of sets. Therefore, all set theoretic operations should be applicable as graph theoretic operations. So if G is a subgraph of G, then the definition tells all edges in G, small g, should be present in capital G. So all edges in the small set G should be present in the capital set G. So edge set, commonality in the edge set should be there. Of course, this edge set is a superset, whereas this edge is a subset, but all edges present in this should be present in this. And vertices in G should be present in G. And each edge of G has same end vertices in G as in G. So that is the correspondence. We will make it very clear with an example. I have not labeled vertices, I have not labeled edges, I have left it to your imagination labeling. So I made it more pictorial over here without labeling them. So here is a subgraph. Okay, this portion here is a subgraph. Let us apply let's see how the definitions are applicable. This edge is present here, this edge is present. So the corresponding edges are present. That's what. It has got many more edges, but these edges surely are the subset of the edges here. Plus the last line, each edge has the same end vertices. So this edge has these two end vertices. Here also in graph G, capital G, the same edge, corresponding edge shall have the same two end vertices. That is the meaning of that. Okay. So again, the vertices, here there are many vertices, here there is a subset of vertices. So there should be correspondence. In fact, this has a one-to-one correspondence with this, whereas this does not have one-to-one correspondence with this. It shows a subset, sub-relationship. This is very, very important in many pattern recognition problems. Many pattern recognition problems. For instance, now all of us are wearing masks, and face recognition is going to be a failure. Everywhere we cannot have iris recognition. Okay, and iris recognition is really difficult, particularly when you wear the glasses, when you wear the spectacles and move around. Camera cannot penetrate into your eyes, and it cannot pick up the eye. You have got to still depend upon the face recognition. But with the mask present, this subgraph will not be available in this graph, in this overall graph, and still you have got to make the recognition as accurately as possible. Therefore, a graph has several advantages. You should be able to imagine the presence of this subgraph in the absence of that subportion in a bigger graph. That's how you can make a recognition. Okay, all right. So here are this, of course, these two are subgraphs. You can see from the picture, these two are subgraphs, and now they are edge disjoint. See, these two vertices are common in both these. These two vertices are common, whereas this vertex is not present here. This vertex is not present here. This vertex is also not present, but these two vertices are common. However, all these edges are entirely different from the edges which are here. Therefore, they are edge disjoint subgraphs. Look at this example. Not only they are edge disjoint, they are also vertex disjoint, because no vertex is common between these two sets of subgraphs. So these are vertex disjoint subgraphs. So this edge disjoint, this is vertex disjoint. Now you can make out that vertex disjoint subgraph should essentially be edge disjoint subgraph, whereas edge disjoint subgraph need not be vertex disjoint subgraphs. Okay, these are all very essential when you start processing the images, when you start processing the video contents, particularly when the robot is moving around. It has got to construct the relationship between various objects in an image, and then it has got to construct the graph, and then it has got to see whether it is vertex disjoint or edge disjoint. Where can I do the correspondence? Can I transmit the correspondence from an edge to an edge through a common vertex, or can I not reach at all? You know, these are the things which a robot has got to decide. Okay, right then. So G, capital G, is a subset of itself. Okay, this is a well-known set theory. If here there is a small mistake, look, if both of them have been written as G, it is not G. If G, if this, let me call this as some G, is a subset of another G. Okay, so this is small g, this is another small g. If G is a subset of a small g, can you understand that? G is, and if G is a subset of G, you see, this G is a subset of this G, and this G, please see my pointer moving around. If this G is a subset of this G, capital G, then this G should definitely be a subset of the same G. That's all. Again, it is a set theory. So every vertex is a subset of G, every edge is a subset of G. When I tell that it is an edge, you should know that it comes with the two end vertices. Edge disjoint, edges are not shared. Vertex disjoint, even vertices are not shared. Okay, all right. So now I shall not worry about the assignments now. I have already given the detailed assignments. Okay, okay, right. I shall skip this particular part which contains the set of assignment. Our people would take 15 minutes time later and then explain every problem also, what is expected of every problem. Okay, all right. So now extract all possible subgraphs containing k vertices. So I mentioned that I want all subgraphs containing 3 vertices, all subgraphs containing 4 vertices, not a specific, all possible. Maybe vertex joint, vertex disjoint, all. I do not I do not mind they being vertex joint, but then all possible subgraphs of k vertices. Okay, all right.